Yeah, sir. Hello.
Yeah, hello.
Yeah, shall we start, sir?
Yeah, we can start it.
Good morning, dear participants. A warm welcome to the Day 4 Faculty Development Program on Recent Trends in Microgrid Technologies by organizing by Department of Electrical and Electronics Engineering, Indian Institute of Technology and Science. A warm greeting for you all. So now we are entering into the Day 4 of this session. So, dear sir, we are welcoming you, sir.
Yeah,
Now I am going to hand over this session to the Dr. Deepak Reddy, sir.
thank you very much. So from the past 3 days, we have been studying all the basic soft microgrid systems, basic device level control and primary control schemes. So today what we will be discussing is about secondary control schemes, how the secondary controllers are designed and what are their roles. And what is how the conventional secondary controls are developed in an existing system, and how the microgrids, how the new techniques of secondary control schemes have been developed to reduce this communication burden and single point of failure issues because of the centralized computers. So let me start with the limitations of a centralized control schemes, which are usually used in power systems. So in generally what happens is, like in a centralized control schemes, single computer will take a single central unit or computer unit will take all the readings from the distinct places. It can be load bus or a generator bus. Then it tried to do the computational whatever it needed. Then it sends a reference signals to all the source points so that they operate at that. So that's how it conventionally happens. Like it means like you have a communication channel between every source to the central unit, and you also need a huge bigger computation unit to compute or to solve that big system and provide a better good optimal solution or better solution. So that's really a very big task, because to ensuring that we have a communication with every source, it's a really intensive communication. So we may need a big bandwidth communication channel, and also a control unit also need to be very bigger in size. Like it has a more computational facility. Like it should be solving a bigger problems, so that it means we need a larger computational units there. So this is two drawbacks. Another drawback is like single point failure. Like if the central computer gets failed, so there no more, it could not able to send any information to all the source points. So which is considerably a serious issue under any disturbance or any damage happens to a centralized units. So that's not an advisable way, and especially in distribution systems where sources are closely bounded and near to each other, sources and other things. So it's better to use a distributed control, distribution communication channels instead of you having a centralized computer, because to make it as we said, it may prone to a single point failure. We don't want that condition to be happen, at least in a distribution level, because when what we discussed earlier, like whenever the systems gets islanded, at least they need to operate it independently without taking without seeking any information from the centralized computer. So to have an islanding operation, again, if we have a centralized computer to share the information and to make them individual source operate, that will be again a computational issue, and that won't be a good reliable solution. So that's why distributed control schemes will be a better reliable schemes to enforce this. So what are the advantages we get from the distributed controls? So first of all, distributed controls are structurally more efficient, and we doesn't need a big computational units here. We can use all the low computational units, which are like general DSP process or PLC circuits at our source points, which can do the sharing of information also, and at the same time it can also do the controlling points also. So it can do it locally at your device level itself, and we doesn't need any system information. Like we doesn't need if the source is connected at any point, or if the load is connected at, like it can randomly come in and start delivering the power and start communicating the information with the other units. So this gives us a plug and play approach. Like anyone can plug and play. Plug and play in the sense like you need not to give any prior information to the system. You can directly connect to the system, just like how we do in the loads. We don't give any prior information to the grid. We just switch on our loads. The same way, sources can also be done. Like it can be directly connected into the system, and it does all the needs what it need to be taken care of. Okay. Now, since we have got plenty of advantages in distributed control, so we need to basically understand what exactly the distributed control schemes are and how we can use these control schemes, how we can use this approach in our microgrid systems and other, especially in microgrid systems. So generally, distributed control schemes, we use multiple agents. They are realized using multiple agent systems. So what does this multiple agents indicates? So let's say if each DG is considered to be an agent, each DG or DE are considered to be an agent, since in a microgrid, we can have an n number of DGs, like we can have some n number of DGs, and each DG now is an agent because each DG also has their own control unit, either PLC or a DSP processor at that point. So those control units can have can do the controlling aspects, the device level control aspects and the primary level control aspects. Now what we do is we are assigning a secondary level control also to that devices, to that controllers, so that they do that secondary level control and they do share the information with the others. So it means it was enabled with the communication, a local communication. So that makes to share information with the others. So how exactly that happens, how exactly that distributed communication happens, and how exactly they're communicating, like are they communicating with one to everyone or like one to one, or like this information need to be known, right? So for example, if you see in this figures 14, these are all nothing but, if you see them, they all are connected. They all are connected directly or indirectly. They are all connected. Like one is connected to 3. So indirectly one is also connected to 2, right? Because 2 is connected to 3 and 3 is connected to 1. So indirectly they are connecting these things. So this kind of structure, what we say where all the nodes are directly or indirectly connected, generally called as a tree, a spanning tree. Spanning tree is like having edges or lines, we can say edges, connecting to all the vertices in the sense nodes. All the nodes are agent points here. Nodes means, so if that happens to be connected with all the nodes, then it is said to be forming a spanning tree. So the basic spanning tree need to be formed for a distribution communication. So we don't expect every DG connected to all other DGs. That makes it more computational. Again, it increases computational burden. So we don't need that. We need only what are the information we need to connect them to one or the other points. Okay. So the DG, let's say the DG1 is connected to DG3, and DG1 is also connected to DG5. So now DG3 and DG5 are called neighbors of DG1. It's not the DG2 or DGN. Although DG2 or DGN might be closer, like as per the distance point of view, they might be closer. But in this control scheme, in this communication control scheme, what we say the neighbors as who are connected to them directly through a communication channel. So they are called as a neighbor, not the one which is closer. So here DG5 and DG3 are neighbor to DG1. Similarly, for DG2, DG4 and DG3 are neighbors. So that's how the neighbors are defined. So the thing is, once we define the neighbors, so how we share the information, how we control the information which has been shared, all with these things we will dealing in further. Okay. So the basic thing is we have multiple agents in the microgrid system, like multiple sources, and each source has a capability of computation. Like each sources can be controllable using the PLCs or DSPs, and these processors or these control units has a communication enabled. Like it has some communication channel which can send information to others. So here others need not to be all, it's only to be some few, like at least 1 or 2 to be connected as a neighbor to individual agent or individual DG. Now, This is simple and this is clear, right? So it is nothing but we are talking only about the graph theory, communicational graph theory. So earlier graph theory we used to use in network analysis. So the same is applied here in the communication. So these are the few notations what we generally use in graph theories. Like if it is a set of n digits, we have 1 to n digits. This is called set, and we do have edges. Edges is nothing but the links that connects links or the lines that connect the multiple digits. So, and the graph theory is defined as a function of number of set of nodes and edges. So that's how we define. These are the basic general notations which we generally use it for the graph theory. So so now in edge set, if you see here edge set, it is defined as an edge if there exists a connection between I and j. Let's say if I and j are the two nodes or two digits, if there is a communication link between them, then that communication link is called edge, and that I and j are called as adjacents. They are adjacents. Neighbor and adjacents are like synonyms, right? So I is neighbor to the j, and I and j both are adjacent to each other. That's the same thing. So based on this edge set and adjacents, what we do is we calculate the adjacency matrix. Adjacency matrix is it's nothing but a incidence matrix kind of stuff, where it's similar to the incidence matrix, like where we, if there is any, it's similar to adjacency matrix, which we studied in network analysis also. So where if we have a line connected between the nodes, then we will be having that value as 1. Like if aij, I and j are connected, then it will be replaced the value of that matrix as 1. If there is no connection between them, if the I and j are not adjacent, then it is replaced with 0. That's how we form adjacency matrix. So now I also described what is neighbors, right? So for each DG, there will be a neighbors. So based on the number of connections established, there will be a set of NI neighbors. So those need to be identified and need to be collected and kept as an information. Although we don't use it exactly, we only use a complete communication graph theory. So that graph theory is only the change we need to think of it. Otherwise, we need not to track all the neighbors and all the information. We need only the graph theory information. So all this information, the graph information, is stored in a matrix called Laplacian matrix. So this L is a Laplacian matrix which stores all the information, like whether they have a neighbor or not, whether how many neighbors are connected. All this information has been stored in this. So this Laplacian matrix is defined as a degree matrix minus adjacency matrix. So degree matrix is that thing, but how the number of nodes connected to the each DG, whereas adjacency matrix is the adjacents, like what are all the adjacents which we have formed earlier. Like, so whenever there is an adjacency matrix, we'll replace that Aij with 1, or if they are not, I and j are not adjacent, then we'll replace with 0. So this adjacency matrix records the information of what are the nodes are connected to the ith DG, and D holds the information of how many nodes or how many DGs are connected to that ith DG. So that's why if I calculate that Laplacian matrix using D and D minus A, we get all the information. Okay. So the peculiar structure and the peculiar thing of L is that it's always positive and semi-definite matrix. Since we are going with a bidirectional, like information can be shared from I to J and J to I. So the Laplace will be symmetric. Since Laplace is symmetric, and since it is symmetric, and it also has a structure like positive semi-definite. The reason being, we are adding the like number of the degree, the diagonal matrix will, the diagonal component of the matrix will be, is a degree in the sense the number of nodes connected, whereas A is all other nodes. So if you see the sum of row, it will be always 0. So that makes it to a semi-positive definite matrix and semi-positive definite matrix especially. Okay, so that's a peculiar characteristics. So the reason having the positive semi-definite matrix and how it will be helpful in how in the defining control schemes, and how it will be helpful in analyzing the stability of the controller which we design, we will be seeing in the next slides. Okay. Okay. So till now, what we did is we understood the graph theory, how the nodes can be connected as per the communication perspective, how the nodes can be connected, how the peer-to-peer communication has, and how this peer-to-peer communication information has been stored in the Laplacian matrix. All this information has been used. Now, how do we apply this to the system or a control? Like, how do we use this for control systems? Okay. So there are few control schemes, which is called a distributed consensus control scheme. Distributed consensus means, the name as indicates, consensus means you need to make an agreement. You need to make an agreement. Consensus is nothing but coming to an agreement, right? So you need to make an agreement between all the sources connected, such that we will reach one final goal. That's what consensus means here. So I will give a basic consensus algorithm, which we usually use in our distributed control schemes, especially for microgrids. There are complicated dynamic consensus algorithms also available, like big state matrix based. So we don't go with that big complicated. We will go with a simple two methods. One is dynamic consensus. Second one is dynamic average consensus. So let me introduce with the dynamic consensus first. So dynamic consensus, in this, what we do is we take the information from the neighbor and we subtract the information with our own. Let's say if I'm an agent and let's say I have 3 more agents around me who are sharing information. So what do I say? Let's say my name as agent 1, agent 2 has something, and agent 3 has some information. Okay. So agent 2 is not connected to agent 1, but agent 3 is connected to agent 1, and agent 2 is connected to agent 3. So it is like we form a basic tree, like 1 is connected to 3 and 3 is connected to 2. So we got a basic tree. So 1 is not connected to 3. 1 is not connected to 2. You need to remember this. Now, let's say now I have a value of 4, some value. Let it be anything. Let's say I have a value of x as 4, but agent 3 has a value of 3. And agent 2 has a value of 5. So let's not complicate things. Let's do one thing. Agent 1 has a value of 1. Agent 3 has value of 3. Agent 2 has value of 2. Let's say 1, 2, 3 has 1, 2, 3. Okay. Now, since information has been shared, like agent 1 is sharing some information to agent 3. What information? Saying that I have number 1, I have a x value as 1. So agent 3, who is sharing the information, he shares that that I have a value of x as 3. So what they do is, now agent 1 is doing the calculations. How they do is, he takes his agent 3 information which he got, he subtracts with his information. So what is the value now he got is 2. So 3 minus 1 is 2. So he integrates that and improves his own agent information. So x new updated will be integration of 3 minus 1, that is 2. So what happens? Integration of this, it comes to be a 2. It comes to be a 2 value at that instant, t is equal to 0 instant. Similarly, now agent 3 is sharing information to agent 2, right? So agent 3 shares information to agent 2 as 3, but agent 2 has 2 as an information. So 3 minus 2, there also it takes like 3 minus 2, 1. Integration of 1 will be the value is stored at x. Now, agent 3 has got information as 1 and 2 because it is connected to both 1 and 2. So it gets 1 and 2. So now it is nothing but summation of agent 1 information minus agent 3 information plus agent 2 information minus agent 3 information. So overall what happens is, so it is like 1 minus 1 minus 3, that is minus 2, 1 minus 2 is minus 3. So overall it is getting into a negative value, right? So now this at the second instant, at the instant of t is equal to 0, agent 3 got negative value, agent 1 has got some positive value as 2, agent 2 has got some positive value as 1 at the instant of t is equal to 0. Now, since integration keeps on going on, x gets updated iteratively. It gets updated iteratively. And finally, it settles to a common value. So all the common value is generally used to be like, it's nearly equivalent to the average value, which initially they hold. So it's 3 plus 2 plus 1, which is 6. 6 by 3 is 2. So they all comes to a consensus such that they settle at nearly 2 as in value at a steady state. So that's how this information is shared. Okay. So that's how it happens. That's what we are doing here. Integration of summation of xj of t and xi of t. So j here is nothing but set of all neighbors. J is nothing but set of all neighbors, right? So if I have 3 neighbors, so it has been 3. Like agent 3 has 2 neighbors, so that's why it has done 2 times, and it's got summation of that, and then it is integrating it. And here Aij, it's nothing but adjacency matrix value, which we usually considered as a 1 earlier. Now, if you don't want to consider them as 1, like if you don't trust agent 2 information, you only trust mostly on agent 1 information, then what you do is your trust has some efficiency. Like you feel that he gives me 50% correct answer, 50% wrong answer. So what I do is I'll give them as 0.5 as value, like Aij as 0.5. Whereas for the agent 1, I'll give as 1 because I 100% trust him. So that's how I can adjust this trust value also, Aij trust value also. Thereby I can do the calculations so that we will all form into a consensus. So we all come, all the agents come into a consensus. That's how it's a basic, simple consensus is something but coming to an agreement to a value. What I have is correct value. So I'm trying to maintain. So all 3 want to maintain x as some common value. So how do? They initially start with some random value or some value what they have themselves. Then they share information with all the adjacent neighbors. Once they got adjacent neighbors, they do this law like integration of summation of all the errors. Finally, they settle to a consensus, like common point. That's how consensus is achieved. This is simple. Like you should understand in a simple fashion. Okay. So that's what we will be implementing into a microgrid also. So as I said, we need not to store all the information of all the nodes which are there. So it's in simplified fashion, how we can write this entire equation is nothing but x dot of t. X dot is nothing but, because we are getting integrated term to the left side, it gets to be a derivative. So x dot of t is nothing but minus L of x of t. Okay. So it's nothing but x of t. It's a state matrix, right? It's a state matrix, means it's single order, first order system. So you can easily solve that. But it is not a single input, single output system. It is multi-input, single output system. That's you need to remember is it is multi-input, single output systems. Okay, you get multiple inputs, you will get a single output. So that's how its system will be. So still you can reduce into a S domain. So I think everyone is clear with the dynamic consensus now for now. So now let's go with the dynamic average consensus. So in the dynamic average consensus, what happens is I estimate an average value inherently. I don't say in this, what do I do is I estimate its total average value. Earlier is like we are trying to achieve a common consensus among all the DJs so that it comes to a common value. In these conditions, the value like values which are held by agent 1, agent 2, agent 3 need not to be a sum divided by 3, sum divided by number of agents. It need not to be a common average value. It may be deviating some between the average values. It may be coming to some consensus itself. There is no guarantee that it reaches the average value. So now in this second case, in dynamic average consensus, what we do is all the information what we there will be coming to an average value. So what is that? What is this thing is here we don't bothered about x. We are no more bothered about x. Although we have somewhat bothered about x, but we are not bothered about x. Reason being, we don't alter x. What we alter is average value of x. So are we having all the like agent 1, agent 2, agent 3? They are estimating some average value. What is the overall average we have holding it? So overall average value can be like agent 1, agent 2, agent 3 holding a 1 to 3 values as then the overall average value is it's 2. So the estimated average value for agent 1 for now is only 1 because 1 by 3 is 0.33. Estimated overall average value is 0.33 for 1. For 2, it is something around 1 divided by, he expects 1 to be there and he expects all other agents also having 1. So 3 divided 3 divided 3, it will be 1. That's what average of agent 1, because he has 1. So he assumes that agent 2 and agent 3 also have 1. So he takes sum of those 3 and got to be an average value as 1 For agent 3, it is 3. For agent 2, it is 2, because they only know their information and they assume that other agents also have the same information, but which is wrong. So average value is 2. So how do they get into average value? Because they share this average information now with others. Like since his average information is 1 and other agent average information 3 and other agent average information is 2, they share this average information. Rather, they're sharing the actual value. And now they do the same algorithm what they did earlier, and they calculate the difference in average. So they calculate the difference in averages by integrating them, and they do add with the original value. So now if I get a value of 0.33 after doing all this calculation, and I will add this 0.33 of agent 1, so that my average value will get into be 1.33. It's not 0.33. So it increases. So similarly, it will be reduced for the agent 3 and it will be increased for the agent 2. So that's how they come into the consensus with the average values. They don't come into consensus with the actual values. So this is helpful where you don't want to change your values, where you don't want to change your original values, but you only want to change your average values. There we apply this. Okay, so I guess you understood what is the difference between the dynamic average consensus and what is average consensus. What is dynamic consensus? So dynamic consensus is changing the value itself. Dynamic average consensus is changing the average value to bring it to a consensus, like to get it to a common consensus. That's it. So that's a simple difference. So here also, as we said, like we can split this entire system into a state matrix. So where now the state of this is average, it's not the actual values. So actual value will be the differential term. Okay, here x dot of E. So this is actual value, but average values will be average estimated values will be used here in a states. Okay, so I think this is clear for you. Now I will explain how we apply this, like where we apply this and how we apply this, what is the need of application of this in the next coming things. Okay, so this is a simple microgrid system. It looks complicated. Let me simplify for yourself. I have a microgrid system, which is electrical network. So I have multiple DGs, DG1, DG2, DG3, DG4. I have loads, and the lines we have, and then we have filters, and then we have like inductor coupling with the network. Like there is a line network, okay, distribution line that connects to the network. So this is simple electrical side. If you see the, I don't know if you identify the color, it is like light pinkish color. So this is a microgrid. This is simple microgrid. We don't have anything, simple microgrid working. So with the electric components. Now each electrical component, each electrical source, DG1, DG2, DG3, DG4 are included with control scheme. So what are the control schemes we studied earlier is primary control, right? Primary control and device level controls. So those primary and device level controls give a reference or PWM signals to this DG. So that's what group control is there here, where they take the information of the local current, like filter current, the voltage across the capacitor, which we studied earlier, and then the output current. The output current used as a feed forward, and they also used as a power calculations. Because output power into output voltage is nothing but power. That's what we seen yesterday, right? So that power calculation is also being used here. So those are being used. So and then the droop technique is implemented, and that gives the PWM. So that's a simple. Now, what will be the reference to this droop control? Will it be, someone should be providing, right? What will be that? So generally we don't take the nominal, we take the nominal values, omega n and Vn are the nominal values, okay? So if you do that, so frequency gets deviated, and there will be a frequency deviation with only droop control. We need to avoid that. We need to get back our frequency to the nominal value. So I need to change the reference value, nominal frequency, which we have to like 2 pi f. We need to change that nominal value such that our actual operating frequency will be at 50 Hz, near to the 50 Hz almost. So we need to change the nominal value of voltage such that our voltages at all the buses or all the nodes with which we are controlling are near to the nominal values. So that's what we need to do, because droop reduces the values from the nominal. So we need to avoid that. So that's why we need to change the references, like omega and Vn correspond to this droop control. Okay, So how do we do that? We use a consensus-based secondary control to change that. Okay, we use a consensus-based secondary control to change omega reference and V reference. At the same time, tertiary control is also used to get that omega and Vn values, which is fed to the secondary control, and combinedly they are shared with the group control. So that's all. So that's what we did yesterday. We studied the hierarchical control like 2 days back. So it has a group control, secondary control, and tertiary control. They are in hierarchical fashion. They share the information and they do work. So that's what we are doing here. This is a control layer where we have a group control, which is already expected to be at device level. So it is at device level. Now we are using a consensus-based control at the device level itself and tertiary control at device level itself. But this is cool. Everything is good. Everything looks better here. Consensus algorithms need some information of voltage and current, so that we need to maintain the power also, and we also need to maintain the voltages. So that's why we need that input. And whereas tertiary control needs some information of power, so we'll take that power input also in the tertiary control. So these inputs are fine, but we also got external inputs, which is solid lines. If you see these solid lines, so these solid lines indicates the information shared from the communication channel. So if you see this bottom rectangle box, this is nothing but communication layer. So this communication layer is nothing but the communication channel, the graph theory, what we studied earlier, that's what this is about. So say like 4 has an agent with, 4 has a neighbor, 4 is a neighbor with 1 and 3, right? So 1 and 3 nodes will share the information to 4. So that information need to be shared to the tertiary control and consensus algorithm, right? So the consensus algorithm, what we studied earlier. So those information will be passed here, like through a communication channel. So I did split it outward, like as a separate block, but in actual, what happens is like communication is already embedded into the control, like communication is in the control itself. But only to differentiate how this working, that's why I made it as a separate block, communication layer block, okay? So it shares the information, and it need to send the information also, right? So it sends the information of lambda, I, omega, and voltages, and reactive power, all this information, like amount of reactive power it's sending, amount of voltage it's sending, it's maintaining, the frequency at which it is operating, and the lambda is nothing but the economical dispatch points, lambda. So which we studied, this is something like Lagrangian constant, what we say. So that information is also shared to have economical operations. So it shares that agent 1, let's say agent 1, which shares the information to 4 and 2. So that's why this has been put into a communication block. So communication, if I put it into a communication channel, so the one who is always continuously reading, he takes the information whenever he wants. So that's how it happens. So this is simple to understand. You just need to visualize things, what's happening here. So we have a network here, microgrid network, and with multiple sources. We have control. We have where the control of basic control is happening, the group control with device level controls. But to do this hierarchical control scheme, we need a secondary and tertiary control, but we are not doing a centralized fashion, we are doing it distributed fashion. So if you're doing in distributed fashion, what we need to do is our secondary and tertiary control should also be there in a local control scheme. So that's why we put them into here. But to have this distributed control work, we need to have a peer-to-peer communication structure, like one DG is sharing information to other, and other information is taken from like other information is also taken. Then we using that to achieve some consensus. So that's the simple things. That's what we are doing here. Okay. So what will be the control scheme internally look like? So this is simple. This is simple schematic, and you can visualize things here. But it gets complicated if you go internally with the control schemes. So I will make it simple. I will make it simple and understandable to you. So you just need to remember the average consensus and consensus what earlier we studied. And you should know that what actually the inner current control and the primary control purposes are, okay? So this is simple network, what we earlier seen, where the VF mode is operated. Like this inverter is operating in VF mode where voltage and frequency are controlled, okay? In this, inner current control, voltage control is simple, which we discussed earlier, like cascaded controls to control the voltage references provided. So voltage references and frequency references are provided from the primary control. This is simple primary control. So what I used here is economical dispatch control. If you see here, economical dispatch group control scheme we are using, which we discussed at the last of our primary control schemes. So that we are using here. So the K is nothing but constant multiplier. K is nothing but that what do you say? That slope, the slope the slope and the steepness what we need to have a sharing proportionally. Okay. So this is simple, okay? And we need to calculate the active and reactive power to share this information. Like we need an active and reactive power to send the troop control, right? So that's why we are doing here. So these still below this, it's simple what we studied earlier, but we're just clubbing them other like device level and secondary level, sorry, device level and primary level controls are clubbed. That's all. Now coming to the secondary control. If you see here, what the main purpose of the secondary control is? To maintain the frequency, to get back the frequency which has been deviated because of primary control, right? And to maintain the voltage which has been deviated. What we do here, we use these algorithms. Here, if you see here, I think you can see this, we got a consensus algorithm, right? So what we are doing here is, at the frequency especially, we have an Aij, omega j minus omega I. So Aij is nothing but the same value what we discussed. It's an adjacency value. How much you trust on the information got from that agent, jth agent. So that's a trust coefficient, you can say, or adjacency coefficient also you can say. So, and omega j is the information obtained from an agent which is adjacent to I, and omega I is your local information. So locally you got some omega I, right? That we use here. And omega j is what agent is sending. Like he's saying that his frequency is for now is around 30, like 49.9, but your frequency is 50. So you will differentiate, you will subtract them. But this will be continuing, this summation will be continuing till all the nodes, like all neighboring nodes have been completed. Like agent I, like for here, agent 4 has, as agent 1 has agent 4 and agent 2 as a neighbors. So it will take as omega 2 minus omega 1 into A12 plus omega 4 minus omega 1 into A14. That's what this summation is, like we are doing for all the agents. So we did this for. Then what is this BII? Why do we got this BII and omega f minus omega I? See, although we are sending some nominal values, reference values, we need exact a higher nominal value. Higher nominal values here is omega ref, which is to be maintained. Like for what is the frequency you need to operate? Like is it not 50 Hz, right? 55 Hz. Although if the difference gets 0, it doesn't mean that it will be operating at 50 Hz component. Like it doesn't be operating at 314.159. It might be operating at 314 or 313 because only the difference is 0, but it's not reached to a nominal value. So what they do is this generally a very trustworthy agents, like who are very 100% trustworthy, they will be provided with a reference value, a nominal reference value. So we will it will be provided with a 50 Hz or like 50. Sometimes a system may need 51 Hz or 50 Hz based on their own needs. So a trustworthy agents, like 1 or 2 agents, will be provided with this omega ref. So the BII is a matrix that indicates the trustworthy agents. So this is called pinning strategy. Like you are like any centralized computer, like even if this is distributed control scheme is happening at the local microgrid level. If you see in the bigger picture of big grid, in the big grid, there might be a reference, an omega reference, omega actually what's happening, that have been shared with omega ref. That information has been shared here through a pinning strategy to a trustworthy who doesn't alter the information and directly send it to others. So those agents have been given with this. So since they are pinned with an information, they are called, technique is called pinning techniques. And the same technique is used for synchronization. So earlier we also learned that secondary purpose is to synchronize with the system. Now, if omega ref is nothing but the grid frequency, it has been shared, and if I try able to track that grid frequency, it means we are matching with the frequency of the system of the grid. Now we can directly switch it to the we can directly get that to frequency. Like if grid frequency is 49.5 Hz, we'll give omega ref as 49.5 Hz, and it will be 49.5 Hz system slowly, and then we can switch it to the main grid. That's what synchronization process is about. So that can be possible. That also can be possible, but right now we are doing it only in a autonomous operation, in islanding operation. So we assume that some information is pinned by some other centralizing unit. Okay. So that's the main purpose of using this pinning strategy. So this is nothing but simple consensus. This is the pinning consensus. So pinning consensus is like the reference which has been provided, it need to be tracked. So that's what pinning consensus is about. So it's simple. So finally what happens is, if even one, because of this configuration, because of this pinning configuration, even ith agent gets to be equivalent to the omega ref, even if ith agent gets to be equivalent to the omega ref, what happens is all other agents are forced to come to a omega ref value because of these consensus algorithms. All other are forced to come to this omega ref value. Okay. So that's how this works. So I think you understood how we applied the consensus, basic consensus, what we learned, dynamic consensus have been applied for the frequency. Now we'll see for the average consensus of the voltage. We'll see how average consensus is applied. First of all, let me tell you why we need average consensus here. Why don't we do this same as a normal consensus here? There is a reason for that. The main reason is, see, in a system where effect-wire ratio is low, we don't expect to maintain the voltage at reference value, and to maintain the voltage at reference value, and to ensure the reactive power sharing. Like they all share the equal amount of reactive power or proportional amount of reactive power by maintaining the voltage at the same value. If you maintain the same value at this point, so it need not to guarantee that the reactive power will be proportional, because sometimes it may go beyond, like it may not do that. So we need to compromise either the reactive power, we need to compromise, or we need to compromise the voltage. So what we are doing is we are trying to compromise in the voltage here. We are trying to compromise in the voltage. How we are doing is, here voltage has between a soft limit, like we need not to have a nominal value. It can have plus or minus 10% of voltage, or plus or minus 5% of voltage. So it doesn't damage much if you have a plus or minus 5% of voltage as a system considered. So what we do is we're trying to maintain the voltage between that range, plus or minus 5% or plus or minus 10%, whatever the grid code mandates us. But we will try to maintain that. What we do is we'll calculate the average value. We estimate the average values of the voltages at which they are connected. And that average value is expected to maintain at reference. It means if we don't, like what is the advantage we are going to do? If you don't do that, if you only do the nominal value, what happens is all the voltages fall down, all the voltages gets down, because of the droop, all the voltages gets down, like they are always lower values. If all they are supplying to the lagging power or lagging loads, all the voltages come down. And there can be a condition where there is a one source which might be coming to almost at the nether point in the lowest point or lowest limit point, so which is not advisable. But here, because of the average consensus, what happens is some voltages will rise and some voltages will fall. Some voltages will be higher, some voltages will be lower to a nominal value. And overall, if the sum is considered, it will be at the reference. Like overall, if you take the average, it will be at the reference value. It means instead of only making all the sources to come down, what we're doing is we are trying to increase the voltages of few buses such that overall the average value of the network is at nominal value. That's what we're doing here. So that's the main advantage, but the main thing why we are using an average consensus here, dynamic average consensus instead of dynamic consensus. As I said, dynamic consensus may not lead sometimes to a proper reactive power sharing. So we need to overcome that issue. That's why we are using average consensus. I guess now you got understood what's the secondary layer doing here. Now coming to the tertiary, that is nothing but reactive power sharing and economical power dispatch. So for economical power dispatch, as per the economical dispatch concept, the Lagrange lambda should be common. If the generation is within the limits, the lambda should be equal for all the generators. If any generator hits its limits, we should exclude that generator. We should not share that information to any other generator, keeping it as Pmax. And then the other generators need to come to be equal lambda values. That's what we do is. So here we are doing the same. Like what we are doing is we are taking the lambda information of all the generator, like all the agent information, and we are trying to reduce that error. Finally, what happens? All the lambda comes to a common consensus value. See, if all the lambda is a common value, it indicates economic dispatch been achieved as per the Lagrange KKT conditions or Lagrange conditions. Okay, this is simple. So we are just using a lambda as a function. Similarly, if you want a proportional power sharing, NQI QJ, NQJ QJ and NQI QI. Here NQ is nothing but the proportionality constant. So one inverter may be having 5 MVA rating, or one inverter may be having 1 MVA as a rating. So NQ will be 1 by 5 and 1 here. So based on that amount of power that can be shared, we need to define that NQI, right? So based on the rating of the inverters. So that's why we, instead of taking QJ and QI, we take NQI QJ and NQI QI. So that proportional sharing happens. It doesn't happen equal sharing. You need a proportional sharing as per the rating. So that's why we are taking NQJ here. So what we are doing is the proportional difference should be 0. The proportional difference should be 0. Okay, that's what we are doing. So what we are making is proportional difference should be 0. So thereby all the reactive power shared is proportional. So indirectly what we have achieved here is these are the objectives what we achieved. One, we achieved our frequency to be omega f. All the inverters frequency get to be omega f at a time tends to infinite. Okay, so all the time tends to infinite is set, but what happens is like it is slower. Although it is slower, it takes some time, but it gets to be done in 5 or 6 seconds or maybe 10 seconds. Infinite is like there may be a very marginal difference because of the integrator takes infinite time to settle to a 0 error. There will be like 1 e power minus 5, 1 e power minus 6 error always exists because of the integrator. So it may be taking some large time. That's why we take it as to get an exact 0, it takes infinite time. That's what we are saying here. Otherwise, it gets to a steady point, or it reaches a steady point at least around 5 or 10 seconds, maybe 10 seconds. That depends on the again time constant at which you are operating. Similarly, the second objective of that, the tertiary control objective is economical dispatch. So we are trying to get an economical dispatch by getting all the lambda values equal. Third, we want to get all the average estimated values of the voltages at each inverter or each source to be an equal value. So even though the voltages of their own voltages are different, we need to get into an equal value. That's why we are doing this. And fourth, all the reactive power. Sorry, this should be NQI, NQJ. I think there is a typo here. So all the reactive power should be proportional. Okay. So these objectives will be achieved. No, it's fine. It's good. So yeah, everything seems to be good. How do I trust this? How do I know this will be working? Someone should say, like, mathematics should be proving that, right? And especially if you want to write a paper, you doesn't say that just propose a work and you say that it works. You should prove that. You should prove mathematically how it works and why it works and how better it works. So this proof needed. So that's why what we did is we took some control, like primary control information, and we are saying how we achieved, like how we got these equations from the primary control itself. So we have taken omega ni, we have taken this omega as this common value, and we as a thing, and we derivated that. So derivation gives me these values. So here the k of lambda I pi, I put it as a control input, u lambda I, whereas omega I other control input. Why I'm putting this as control input? Sorry, controller output. Just like how we did it for a current controller and voltage control, we take that controller output as u, right? So that's the only reason why we take this u. So which controller gives this u? That controller is consensus controller. Which controller gives? So this gives me a u and u. So that's why we take that u. Now u is nothing but, so we know the consensus, right? Consensus is, if you state in a consensus, what we did lastly, what we got into conclusion is x dot of t is nothing but minus L of t. X dot is minus L of x. That's what we got. So the same thing, since we know the u, you get that u from this equation. U is nothing but lambda v, because we know that lambda v is nothing but u. So we use that consensus algorithm. Similarly, for the frequency, we use that. Now we need to prove that they reach to a steady state. They don't oscillate or they don't go to be unstable, right? How do we prove that? So you know that Russian author Lyapunov, one of the great author who gave the modern control theory, nonlinear control theory and modern control theory better vision. So we use that Lyapunov techniques. So what does Lyapunov says? Lyapunov says that if I see a energy function of any state, if any randomly picked state, if I see that energy function or a function of a state, if I take that value, and if I see that there will be always, like, if energy function is usually a positive function, right? If I, the differentiation of that energy function, because energy function positive reason being, we always take energy as a square, like Li square. I is a state, Li square, and Vc square, Cv square. Ca is a constant, whereas V is nothing but a state. So it's always a state square. So what happens when even the V is negative, square will be positive. So energy function will always be positive. So we'll take an energy function that is greater than or equal to 0, which always happens. Now we have taken the energy function. If that energy function differentiation is negative, if the energy function differentiation is negative, then we call it as a reducing system. Like, if, see what happens if I have energy and if I have a slope also positive, slope of energy is also positive. It means like energy keep on increasing. If energy keep on increasing, it goes to an unstable point, because it's keep on increasing, it monotonically increasing, it means it's unstable. But if my energy is at this peak point, but it has slope of decreasing nature, so it means like it may be steady at value and then it keeps decreasing at smaller rate. It means you're saying that although it has been increased for a while, but it has a capability to decrease because of the negative slope. So that's why we need to take the derivative of that energy function and need to prove that it is negative. So all we do is we differentiate it, we take it some manipulation. What finally we get is, we get in the function of error is nothing but a state function, which is usually considered to be positive or negative. It depends, which is positive because we are having error square. E omega t and into E omega is nothing but square. E lambda t, E lambda transpose and E lambda is nothing but square. So these are squares. So it is definitely going to positive. Whereas L plus G and L plus G and L, if they are positive, since minus is multiplied here, it means they are negative. If this total expression will be negative. We know that E omega is positive, E omega square is positive, E lambda square is positive. We just need to know that L plus G and L are positive, so that we can say that overall function will be negative. So earlier we did a peculiar structure of L, right? What we discussed is the system L is symmetric, positive definite, positive semi-definite, which implicates that L is positive. That's good. L is positive and everything is. But what about L plus G? So G is nothing but is obtained from a pinning strategy. It means it shares the information. When it shares the information to a pinned trustworthy agent, then we have a positive value. If it doesn't share, it will be having a 0. It means a diagonal component. G is nothing but a diagonal matrix which has a positive diagonal. If since L is positive and G is also positive diagonal matrix, adding both of them, because if diagonal is more positive and getting more dominated in a positive direction, adding both them will also be a positive semi-definite. Adding both them will be positive semi-definite. Sometimes it may be positive definite, but it will be positive. So this indicates L plus G is positive and L is positive semi-definite, which indicates V is negative definite. It means it's keep reducing now, slope is negative. So thus we can easily say that energy comes to a 0, which means it's steady state, it comes to a common steady point. That's how we can prove from the Liouvnin theory. So I think this is a basic control, nonlinear control theory, which uses in the nonlinear controls. So the same goes with the reactive power. We take again the reactive equations, then we do it for average consensus. All these things will be keep going, and we do. So instead of earlier, to a better vision, instead of using the simple Liouvnin techniques, energy function, here I did it with a time varying function. Instead of taking that, we are taking as a time varying function, and we finally say that it is always bounded and it will be always within the bound. Here we are not saying that it will always converge to 0 value. Instead, we'll say that it will converge to some constant value, because we are taking an average value. It doesn't need to be coming to be a constant value. So it will be coming to some average value. That's it. So we say that it is bounded, ultimately bounded, but it won't go to unstable. It won't be increasing or raising function. It will be bounded value. That's what we are proving here. Okay. So to Q, actually what happens in the system, what is the difference between the droop control, optimal droop, full control? I've plotted some results. So, okay. If you see here, there is a conventional droop. Conventional droop is nothing but we just droop the value to certain values. So there will be proportional power sharing, and there will be proportional, they try to have a proportional reactive power sharing and everything, okay? Now, if you see with the conventional roof, what happened? Frequency dropped from 314, like I took it for 50 years. So 50 years, omega should be 314.159. So it dipped almost to the 313, okay? Economical dispatch, they are not, lambda is not equal. They are not equal, it means they are not economical, because the more costlier generator is providing more power, will be providing more or less power. Okay, like this is more costlier, even then they are providing the same power. We should have generated more power from the orange one, but we are not doing that here. During this, what happened to the power? Power is equal because we are expected to be proportional sharing, right? So we assume that all the inverters are at the same rating. That's why we took same values. So it is same power. Now, if you see here reactive power, although we have a dip in the voltage, we are not possibly able to achieve that reactive power sharing, because as I said, the voltages can be different in the system. Voltages can be different at the different nodes. What only we can make sure is, we can make sure only the respond, like they can respond to the changes in the voltages. So they need not come to the closer value of the reactive power. Like they know not to be the same reactive power sharing happens with the conventional roof. That's the problem with that, especially. Voltages, they are exactly maintained at 310 volts, which you are expecting. There is harmonics, there is noise, obviously, because we are completely dealing with inverter dominant systems. There might be there will be harmonics. So don't bother about the small harmonics, but they are almost average values maintained at 310 volts. Okay. And these waveforms are unfiltered. So that's why you will see more harmonics here. So I took the actual values, what exactly happening at the outputs. So that's why we are having some harmonics here. Average value, since all are same, so average will also be the same at 310 volts. Okay. Till here it's clear what we are doing here with the conventional group. We got some negative effects, like frequency is deviated. There is no economical power sharing. Reactive power sharing is not proper. Only thing is voltage, although they are deviated bit value, but they are around 306 or 307 values. I don't exactly remember what exactly the value is. They are expected to have 310 volts, but they are not having that. Okay, so that's what's happening here because of the voltage dip. Okay, sorry, because of the conventional loop. Now, what happened with the optimal control loop? Optimal loop is only we are altering the droop constant of an active power. That's it. We are changing the active power droop constant. If this, what we able to achieve? Nothing, because as in the frequency, if you see, there is nothing improvement. Frequency is still dipping. I took the K constant only to reflect the same value of K, so that we have a same amount of frequency dip here. Because we are assuming that that is a more sensitive point, at that steep value, at the slope value. So that's why I took the same K. So frequency dip still exists, but here optimal loop, because of the optimal loop, lambda should be equal, right? So we got that lambda as an equal value. If you see here, we got that lambda as an equal. It indicates the costlier one will share more power, less power, like blue one is sharing less power. Orange one is sharing more power, indicating that costlier one is sharing less and cheaper one is sharing more. And we are coming to an optimal power. Reactive power, there is no reactive power sharing happening here. Sorry, still, because still we are dealing with the same. So it will be the more or less same because of there is no reactive power sharing. But if you see there is a small turbulence or small deviation from this, do you know reason? The reason being, although they are decoupled, all the explanations, but there is an R which changes the voltages if there is a change in active power because of the presence of R. That's why we are seeing the small changes in this reactive power, only because we have an R in the system. Okay. And the last, full control, where we have secondary and tertiary control, where we have everything like what we discussed earlier. Under that condition, we are getting a very beautiful waveforms. Like if you see, frequency is got to a 314 nominal value, which I provide as a reference here. Economical sharing is happening perfectly. And then full control, what happened? Here we are doing economical control. And why we have these oscillations? The oscillations are because we are having a sudden changes in the reactive power. Now we are trying to push that reactive power coming to the common value. So we are trying to push that. When we do that, I said sometimes it's not possible to achieve both reactive power sharing and voltage control. So the voltage is getting a bit of deviated. Like here, if you see, purple line is got above 310, blue line got below 310, but average value still it's hold at 310. Average value it still is holding at 310. That's how it achieved. That's how we achieve all the objectives what we discussed earlier. As I said, the time here it taking almost less than a second, I guess. Yeah, it's taking less than 0.5 second. So to achieve that consensus. So, but if you zoom in that figure, I don't have a zoom in version, but if you zoom in that figure, there will be a small error, a very small error, like maybe 10 to the power -3 or -4 error. It takes some time to get it to 0 error. So that's the thing. So till here, what we discussed the consensus. Okay. So for you guys, actually this is for the AC system right now. So we will be doing with the DC system tomorrow. So as many people are requested for a case study, requested for a case study, I have taken a simple DG system. I started with the device level control itself. So I could have able to do only the device level control yesterday. So I will show both the equations what we used to design here. What are the equations we used to design here? For the actually this is VF control itself. We are doing it only VF controller here. So I will show what exactly we are using to design this and how I designed exactly in the Simulink. So yeah, coming to the current controller. Let's start with current controller. So how do we design current controller? By selecting a time constant tau c, and LF and RF are already given. So we need to take the KPC and KIC. Okay. So let me go in deep what the exact system is. This is simple DG system where we are controlling the voltage and frequency. Okay. So I have a simple inverter. It's similar to the schematic what I've shown. Inverter, DC source. This is a measurement block. It just measures current and voltage information, which I need to control. LC filter. If you see, I have an LC filter. I don't know why this is. So this is L and this is V. LC filter I used. L in series and LR in series and this thing. And then I have a measurement to measure voltage and current flowing out from the system. And then this is not a filter. This is just a coupling inductors. I just copied the block. So that's why it got an LT filter. So let me correct this. Line impedance, let's say. Okay, this is, by the way, are you able to see this? Please someone let me know if you are not able to see this Simulink block. Hello. You can chat in chat box also if you can able to see this. I'm not sure whether you are able to see this. Hello. Yeah. Are you able to see this MATLAB?
No, sir. Only slide is.
Oh, okay. That's why I want to confirm that. Okay, I will wait a second. I'll just change the sharing mode.
Yeah, sir. Change the sharing option.
Yeah. Okay. I'll change it to the screen, but I think, yeah, I'll change it to the screen. Okay. Yeah. So I think now you are seeing, right?
Yeah, yes, sir. Now it is okay.
Yeah. Let me put it over top for now. Okay. Yeah. So, again, I will come again. So this is simple system. So what we did is we have a DC capacitor here. We have an inverter, 3-phase inverter, which is readily available in the Simulink blocks here. So then we have a measurement block, which is also readily available, which measures VABC and IABC information. We are using a LC filter. Just a second. Yeah. So this is Simulink library where you can find all the units. So I hope you all know this. Yeah. So in this LC filter, we're using L and C. Then I have to measure the voltage, because here I'm measuring the current, filter current to control the current control. And here I'm measuring the voltage because I need to control the voltage, and also measuring the current to make sure to calculate the power if I'm going for a droop control. Okay. And then this is a line impedance that is connected to the network. This here it is a network terminal, so it is connected to that. So overall, this block is like I designed a one inverter model where I have a control and we have a circuit. So this externally to define a network, what I did is I connected a couple of load here, like one linear load and one non-linear load. Okay. So yeah. Now there is an output controller, voltage controller, and inner current controller. The outer power controller, what does it is? It is nothing but a droop control. If you see here, this is nothing but a power measurement. I'm transforming ABC to DQ first of all. Then once I got a DQ, VOD, IOD, VOQ, IOQ gives me active power. VOD, IOQ minus VOQ, IOD gives reactive power. So I'm calculating the this way. Here will be an active power and here will be reactive power. But I said there will be harmonics. As you've seen the voltage earlier also, it has some harmonics, right? Thus high frequency harmonics causes, they may jeopardize the system operation. So I don't want that to be done because even in a small value of harmonics gives a larger deviations in frequency, which will jeopardize the problem. So what I do, I design a filter. Since my operating frequency is 314.159, I designed 10 times of its frequency. So I designed 31.41. So I designed a filter with cutoff frequency as 31 radians per second, like that is 5 Hertz. This filter out the power harmonics oscillations. What are the oscillations which are there? Like high frequency oscillations that have been filtered out. And that has been multiplied with the droop constants, NP and NQ. Those has been multiplied with droop constants. And these values, this value of droop constants multiplied with power is been subtracted. If you see, it has been subtracted from a nominal value of frequency. So here omega I took us to 2 pi f, but if you go for a higher level, this omega will be provided by the secondary control or some secondary control especially. So here also the voltage I took as 310 volts, 310 as peak value. So nominal value will be 220 volts, like RMS value, single phase RMS value is 220 volts, nearly 200 or 220 volts. Okay. So taking this 220 volts as a normal value, peak value, VOD is nothing but peak value. So root 2 times of 220 will be 310, nearly 310, I guess. So that's what I took here. So then it's been provided here. So anyways, I'm not using droop, so that's why I don't bother much. But if you want to use this, you can directly connect it to here. So I've given multiple testing here. So leave over this. This is nothing but simple ABC transformations, which these are an extra, which I'm just checking out whether all the values are coming out good or not. So this is output voltage controller, which is nothing but a droop control, which gives me a reference of voltage and frequency. Omega means nothing but frequency. I got voltage difference. And so if you see VOQ ref, it's usually kept to be 0 because we are trying to synchronize the system. So VOQ ref usually has to be kept to be 0. It's nothing big deal if you don't consider that VOQ. Okay. Now voltage controller. Voltage controller, I have a omega CN cross coupling here. See, if you see, have a cross couple here and here. I have a feed forward controller. IOD and IOQ has been used in a feed forward controller, which is exactly same as here. If you see this, exactly same. Oh, sorry, this. If you see voltage controller here, it is exactly same, right? We have a cross coupling term. We have feed forward term, like we have a cross coupling term. We have a feed forward term, right? Then we have a PA controller. PA controller values, I have KPV and KIV. So what are those values? We need to calculate how we calculated that. I will show you later. So it is nothing interesting. It's the same thing what we studied earlier. Okay. So yeah, here it is omega n multiplied CF. So I think you understood everything here. So that's what voltage control looks like. Current controller. So I transformed ABC, ILBC, because I need to transform it to DQ, right? For PI controller to act. So I converted into ABC to DQ. So this ID and IQ have been supplied to here. If you see, ILD ref, ILQ ref are provided by the opto controller. This ILD ref, ILQ ref are provided by the voltage controller, and we submit, we pass it through the inner current controller. The error is there, and PI controller we have the same cross coupling here, just like here, cross coupling omega LF minus omega LF, and then we have a feed forward terms VOD, VOQ, just like here. Good. And then we have a gain. So you can either see, you can do this VDC by 2 either here or here. It's one and the same. And we are just manipulating the magnitude, right? So we can do it here or we can do it here. I did it here, no issues. Then I transform it to a modulation index. This here it will be VIBC ref, and here it should be modulation index. And that modulation index has been directly fed to the PWM generator. PWM generator is nothing but you will save some switching frequency and sampling time to operate. And then it is 3 arm. We are using 3 arm 6 pulse bridge. So we just need to do it that. That's it, simple. So that has been with a delay time, because our controller should be always slower compared to the actual. If it is in real time, if it is in a hardware, you need not to add this delay. Since it is not a hardware, what happens is this gives an error if you don't have this delay. So that's why, because I need to have a delay between the measurement what I read and doing this controller and what the PWM I'm sending it. So that's why I used one small delay here. So that's only to do that perfect. So about that algebraic loop, I think if you are familiar with any algebraic loop, like, because to differentiate something, we need some initial states. But if there might be some conditions where we don't need to differentiate, we just need to multiply that. Under that conditions, the measurement is taken from there and multiplying it. And I'm using this as a forward term, feed forward term, like to feeding this. So it doesn't know where to start. So then it comes to a loop where it is called algebraic loop. Okay. So if anyone has any doubts in algebraic loop, later I will discuss in better way. But this is how it is. Now coming to the tuning. If you see here, again in the KPI, KIV, I used variables of KPI and KII. I didn't assign values yet. And if you see LC values here, I didn't assign any values yet. I've just given L and C values, constants. Where I am assigning all those values, you can directly assign them. It's not an issue. But I want to calculate them because I want to do it as mathematical as possible. What I did is, first, I took a switching frequency. As I said earlier, I took a switching frequency, which I fixed it on 5000 hertz. You can increase if you want. 10,000 hertz is also good, but I took a 5000 hertz switching frequency. Now, I need to know that sampling rate at which I need to operate. So earlier I said, like, switching frequency should be around 10 to 20 times of your sampling rate, right? So I took the switching frequency divided by 20 times. So that is what sampling rate I got. So entire controller, entire simulation will be sampled at this rate. TS controller is also same as TS. So entire controller, all these things happening at this sampling rate. Okay. So 20 times I've taken. You can take it to 10 times, but 20 times I got it to be optimal value to be 20 times. LF I've taken as 3.35 frequency. Capacitor I've taken as 80 microfarads. So generally AC capacitors will be in a range of 50 to 100. So you need not to use a big bulk capacitors as in DC, because DC we use polarized capacitors. So polarized capacitors will be in smaller size, whereas compared to the non-polarized. Non-polarized are like AC capacitors. They are very bulky if you go for higher capacitors. So you don't use them. You use non-polarized only in a capacitor banks, that too in substations which will bulky, where you use based on the kVAR rating. So you use around 500 kVAR or 1 MVAR rating. So that will be bulky. So here it is 80 only to filter out the harmonics. So it is sufficiently big. Even we can go for 50 or 30 also good, but 80 is sufficiently big if you consider megawatt systems. So LC is a coupling inductance which is connected to this. So RF is the internal resistance of the LF. It can be internal resistance or it can be connected externally, but here I assume that it's an internal resistance which is of 0.1 ohms. So this is the initialization of parameters. I just initialize what are the parameters I'm using for the system. Now I need to design the controller. So designing the controller is simple. What we are doing here is we are following the rules, what we discussed earlier. So we have a LF, we have tau c. Tau c is nothing but controller time constant. So we need to select the controller time constant. Then we need to do it with LF by tau c and RF by tau c. If you see, I've selected omega ci. If you see, I've selected almost 2 into 2 pi. 2 into 2 pi is nothing but 10 times, or like more than that, like 3.14 into 2. So overall this value we have selected. Oh, sorry. I've selected only 2 times because I want my omega ci to be very faster. So I took omega ci as 2 times. If you take it as 4 times or 3 times, it will work. 5 times also it will work. So don't take it 10 times because it takes too much of slow. It will be too slower and voltage controller may be jeopardizing things. So take it 2 times, 3 times, 5 times, that will work. So play with this. You can play with this. Like you can change, like don't take a fraction value, take a integer value and play with that. You will find the best suitable values for this. So don't take it 1 as a switching frequency because it is way faster. Take it twice, thrice, 4 times, 5 times, that's your wish. Based on your performance, how good you are getting that results. That's how you can take it. Now, once you have fixed that omega ci, that is nothing but you are indirectly fixing that tau c, tau I. Now, 1 by omega ci is tau I. LF by tau I is nothing but omega, LF into omega ci. RF by tau I is nothing but RF into omega ci. So that is what kpi and ki. So I used the same variable names. If you see here, I'm using the same variables as in given in earlier. So it's the same, one and the same. So that will be fed directly there. That will be taken directly there when I'm running the simulation. So that's clear here. Now we need to go for the voltage controller. I think current controller is simple, right? I just need to know the time constant. Now, what we discussed. So we discussed earlier in the voltage control design, we should make sure that omega gross or gain crossover frequency should be equal to the peak value, like the peak value of where maximum phase occurs, right? So we calculated that maximum frequency, maximum phase frequency, like the maximum value of, the value of frequency at which maximum value of phase comes. So we calculated that. That happens to be coming as 1 by root over tau c and tau v and tau c. Here I used the term as z for 1 by tau v. 1 by tau v I used as z, like 1 by omega cv. It should be like nearly to omega cv, kind of. Okay. So what happened here is I took that z, then omega cv, that is omega m, is obtained to be as square root of z by omega ci. That's what we are doing here. 1 by tau v is z, 1 by tau c is this. Okay. So this is simple, but we also mentioned that phi m phase margin should be selected by us. If you know, if you remember, if you get it into this, I said that phase margin should be selected between 30 to 70 degrees, in between any value. So I have taken a random 53 degrees. Okay, so once I know the phase margin, I can calculate this z. This can be simplified in terms of, because this can be simplified in terms of sine and cos. Like I can do it 1 minus sine d by 1 plus sine, 1 minus sine phase margin by 1 plus sine phase margin. That multiplied by tau I, because I'm taking tau I as common. So we can do it. This can be simplified as this. If you have any doubt, you can note it down and you can simplify, you will get this. Okay. So I got this phase margin here as this. Okay. No, sorry. I got this tau 1 by tau v as this. Okay. 1 by tau v as this. So now as just simply I substitute that phase margin here. I get z. Using that z, I got omega cv, which is nothing but root over 1 by root over tau c and tau v. And now I need to calculate the kpv and kiv. Kpv I got from the calculations. What do I get? Cf into omega c. Kiv, what I got is kpv into tau v. Kpv into omega v. So that's all I need to do. 1 by tau v is nothing but z. That into kPV, I got tau V. kPV is nothing but CF into omega CV. Omega CV and omega GC are same, right? That's it. So I got kPV, I also got KIV. That's it. What are the things we need to calculate? That's it, right? So once we're done, we are done. We can directly run the system and check how the cell performance is. So I'm running the model now. So let me see, let's see, is it good, bad, worst? Let's see how it works. Okay, so simulation has started. It's smooth, no errors because I already tested it. I already debugged all the errors, so I don't find errors while running in the while giving a tutorial demo, obviously. But obviously, when you do, you will be getting at least even after like I'm working in Simulink after for almost 8 years. Even then, for the first time always I get errors. So don't bother if you get an error. So keep debugging them. That's it. So. Yeah, what did I do? I did it run it for 6 seconds. So you might have confused why I got this wave of sinusoidal. It should not be there like this, right? So thing is, there I'm switching a non-linear load. If you see here, I bet we don't even measure this good sinusoidal waveform in a power supply. So it is pretty good if you see. Even current, see, it's almost like as smooth as like that exact sine wave. This is what the sine wave looks, okay? So it is, since I maintain 310 volts as a peak, 220 volts an RMS, so 310 has got peak, and I'm delivering almost 2.5 amps peak value like of current, which I might be made of 1 kilowatt or 1 kVA, I don't remember exactly the load. Now, what I'm doing at t is equal to 3.3 seconds, if it's 3.3 seconds, I'm connecting a nonlinear load, uncontrolled nonlinear load. I'm connecting a switch, which is here freewheeling diode acts to feed this load resistance. That's why what I got here is after 3 seconds, harmonic currents. Obviously, we can't eliminate. Someone should, some source should there to supply that harmonic current, right? So that harmonic current is supplied by the only source which we have, that is inverters, one inverter. So that's what we are doing here. Now, how can I design multiple inverters? Nothing simple. Copy this inverter, paste it, give some reference frequency. That's it. And connect it. You have 3 ports here, ABC, connect it through a network here like this. That's it. Your inverter 2 is ready. Now, selecting the MP value, you proportionally set the power. Simple. So building a first block will be always tough. Once you build this, you can do it for n blocks, like you can connect them cascaded. You can connect them to the network, okay? So that's how for this today session, I think I'm almost with the time. So I will give 10 minutes of time to discuss, like if you have any doubts or any questions, let me know if you have any confusions. So session is open for the participants to talk.
Yeah, dear participants, now you can ask the questions. I'm unmuting you. You can unmute and you can ask the questions. Sir, Deepak sir.
Yeah.
A question from Anil. Any textbook for power quality issues and mitigation in microgrid systems?
No, actually, I'm not aware of any good textbook, but there is one textbook from Professor Beam Singh, not especially for microgrids, it's for general systems. So So Professor Bhim Singh from IIT Delhi, he worked like, he has intensive experience of almost 20 years in power quality, and he have got tremendous good books with various numericals and experimental results. So I think you will find very interesting if you refer to his books.
Okay, sir. You can ask the questions.
I don't know, no one is asking question. It means like they understood the simulation very good.
Yes, sir. Sir, how to decide which level of inverter we are using? Any reference is there from Kamaksha Prasad Sahu?
So actually there is level of inverters. See, so the multi-level inverters is not at least not my cup of tea. So what happens is like multi-level is especially is to reduce the switching frequency, reduce the switching oscillations and harmonics. So that's why they go for multi-level. Like they use multiple levels. But what if I did is usually I use a high switching frequency, like 5,000 hertz is like good amount of switching frequency. So there will be good amount of losses. But I usually work on this control strategies and this level. I never worked in multi-level. So maybe I'm not a good person to answer this question. My domain is not in this. So usually I use a normal 3-phase 6-switch inverter systems.
Nice session, sir, especially the MATLAB case study. Okay, next. Sir, one question from Venkatesh Challa.
Okay.
In different renewable energy sources, are there what changes to be made in control scheme?
Different renewable sources.
Yes, sir.
See, this is a good question actually. See, for DC volt, say for PV systems, what you have is DC voltage regulator, which we discussed in the second day. We discussed finally that DC voltage regulator, right? So we use that control scheme, and if you use EFIG, even DFIG, there will be grid set converter and machine set converters, right? So machine set converter has one purpose to regulate the voltage, and grid set converter has one purpose to regulate the voltage, whereas machine set converter, it's used to MPPT, like it's operated in PQ mode generally. So there we use PQ control and VDC control both, because we have two converters in DFHs. So, and battery systems, they are bidirectional mode. So they can be used in VDC control mode, VF control mode, because they can be act as a dispatchable source for a short duration time. So they can also be acting in a VF mode, and they can also be acting in a PQ mode. So it depends on the what necessity is there. But especially PV and wind, someone should be there to hold to maintain that DC voltage.
Dear participants, you can unmute yourself and you can speak or you can ask the questions in the live.
So, and one more thing for all participants, those who are willing to work in microgrid systems. So distributed control schemes are the new things which have been studied from last 6 years or 7 years. So there is a vast scope, even if you want to work in that, like there's a very huge big scope in that. So make sure you understand everything clear. It is very simple if you understand it. So you can work on those things. So my contact number and my contact details, everything is available in my website. Please go to the NITW website and search in electrical department. You will find that. Okay. So whoever willing to contact me, you can contact there.
Wonderful session. Yes, sir. Okay, sir.
So, okay, it's so optimal time. So 12 exactly. Yeah.
Thank you, sir. Thank you for the today's session.
Yeah.
We'll
So,
see you tomorrow. Sir.
Yeah, sure. Thank you. Thank you very much. So tomorrow's session will be a shorter session, and tomorrow and day after tomorrow sessions will be a bit shorter sessions. Like I will take only 40, 45 minutes because it's almost like what we did till now will be applying for the DC systems. That's it. So don't worry about those things. Those will be, like tomorrow, most of the time I will be clarifying the doubts. That's what I planned. Like last 2 days, we'll be giving most of the time for the clarifying the doubts. If someone is implementing in their simulations, they can ask me any doubts in the simulations, or they can ask me any doubts in that conceptual point of view also. So tomorrow I will spend most, like at least 15 to 20 minutes. I will give it for the discussions. Okay.
Thank you, dear participants. See you tomorrow.